right, let's jump right into these practice problems. So we're looking at, again, examples of this basic equation ax is equal to b. Again, we have three possibilities. If a is 0 and b is 1, that basically says that 0 is equal to 1. There's no exact solution to that. That's an inconsistent set of equations. So there's no solution, no exact solution. This is a case if a is equal to 7, the number 7, b is equal to the number 13, x has an exact solution, 13/7, and there's only one solution to that. An infinite number of exact solutions. If a is this row and b is this number, that basically corresponds to having a two equations and one unknown. And there you have an infinite number of solutions. All right. What about, we want to model this relationship by the data. So here's x and y. We want to use this hypothesis, y is equal to mx plus b. We've seen that we can stack the data into this regression form. So here's the b, here's the x values, here's the y values. And so the normal equation says this: a adjoint times b x star minus b, so that capital B here is the little b. A adjoint times this must be equal to 0. Multiplying, in this case, A adjoint is just A transpose. So multiplying through by A transpose, we actually get this equation. And so we can solve for x star from this equation by multiplying through by the inverse of this matrix. And that actually gives us the pseudo-inverse. In this case, A transpose A is given by this expression. Its determinant is given by this. And so x star, which is this inverse, A transpose B, gives this expression. And so we have an exact solution to this problem. So again, for this equation, the x star, which is m and b, is equal to A pseudo-inverse times b. So this is the A pseudo-inverse times b. And so going through and calculating, this is the result we get, which should be the same as what we got over here. All right, let's look at another problem. Here, b is not in the range of a, and so the optimum solution is x star is equal to A pseudo-inverse times b. We define our projector. A is equal to A pseudo-inverse. In this case, this is our pseudo-inverse, so this is the matrix that we get. Over all possible x, the one that gets the closest to b is x star, where x star is equal to E times b. So the projection of b, where b is this quantity. If we compute the error, EB minus b, this is what we get. And if we take that, we find that the normal equation is satisfied. That is, A transpose times that error is 0. So that's another reason why it's called the normal equation. It's because it's actually orthogonal to A transpose. Here's another example. Suppose we have this data and we want to fit it to this hypothesis. That is, we want the coefficients, the smallest, and the fit that we want is such that the smallest coefficient values are obtained. So it turns out we have an infinite number of solutions to this problem. So putting this data into the hypothesis, we have this. A solution to this problem is given here, but it's not necessarily the minimum solution. It's just a solution. So we now seek the null space basis. So one way to find the null space basis is to take this matrix, multiply by some vector to give 0. And so that gives us 2 equations and 3 unknowns, which can be given by this expression. It turns out that we get redundant information, and so we only end up with 1 column. And that column now is our orthogonal subspace matrix. So if we let x be x naught, the x that we chose previously, and then we add this quantity onto it, this is a general solution to our problem. So in this case, for any r, this will solve our problem. So if we take this equation, for example, multiply through by a times x plus a times x naught, plus this quantity, A times A perp times R. A times A perp is 0. A times X naught is B. And so we see that this is also a solution regardless of R. So we have an infinite number of solutions, and this is how we can see that infinite number of solutions. Now we want the solution that gives the smallest x in norm. So we take the norm of x. So we have this expression. Here's x. We take the norm of that squared. That gives us this expression as a function of r. I simplify it, and I get this expression. I then perform completing the square with respect to r, and this is what happens when I complete the square. And when we complete the square, we can see that when r is equal to minus this quantity is minimized, and so we get that. The norm is that. So with this value of r, this is the x we get. These are the numerical values of that. With this norm, the norm is this quantity, whereas the original x naught, the norm was 20. It's clearly greater. So this gives us a smaller norm. What about the overdetermined case? We saw that with the overdetermined case, we had this matrix. This was our solution map, and it satisfied this equation for any values of alpha and beta, showing us that alpha and beta are not unique in terms of the solution map. Okay? So if we go now, we take this matrix A and our solution map B. So here, now I have chosen a particular beta in here. Okay, so I've chosen a particular value of beta. And I've chosen the beta so that this matrix B satisfies these three equations. Okay, A is equal to ABA. The quantity AB is self-adjoint. The quantity BA is self-adjoint. So those are three properties of the four defining properties of the pseudo-inverse. Okay, and so for any alpha, I can satisfy these three. So what that shows is that there are an infinite number of solutions to these three equations for this problem. Okay, so notice that these two equations are used for the overdetermined problem. This and this are used for the underdetermined problem. And so this B will satisfy as the solution map for both of those problems. But notice it's only using 3 of the 4 defining properties for the pseudo-inverse. If we look at the fourth condition, that is BAB minus B should be 0, if I form this quantity, it turns out I can factor out the quantity alpha minus 1/5. So this can only be 0 if alpha is equal to 1/5. There's one value of alpha, in which case we get this value, and this value is in fact the pseudo-inverse of A. So this again shows that the pseudo-inverse is unique. In order to satisfy all 4 properties, there's only one matrix that will satisfy all 4 properties. All right, now given this matrix, we see that these 2 columns are independent. So I formed this matrix. Okay, I can show that this column is the sum of these 2 previous columns. So it is dependent. So I choose just the independent columns to form my matrix F. This matrix F spans the range of A. The range of F is equal to the range of A. We now take the pseudo-inverse of this matrix using this formula. Okay, and we get this quantity. Note that F pseudo-inverse times F is equal to I in this case. An identity, actually 2 by 2 identity. Thus, when we take F adjoint times A, so A is equal to F times G, we don't know what G is yet. But if I take F adjoint times A, F pseudo-inverse times A, I know what F is, I know what A is, I know what F pseudo-inverse is. I can compute this. So when I do that, notice that F pseudo-inverse times F is identity, so all of this just gives G. So this is one way of obtaining G, multiplying A by F pseudo-inverse. So when we do that, this is the G that we get. We can go through and compute the pseudo-inverse of this matrix. This is the quantity we get. And so the pseudo-inverse of A can be computed as G pseudo-inverse F pseudo-inverse, and this is what we get. All right, moving on to the next example. Again, AX is equal to B is what we're looking for. Here's our A, here's our B. We're looking for all solutions to this problem and the least square solution. Okay, so for this particular A, I can see that these two columns are independent of one another. I can see that this column is a multiple of that column, and I could go through and show that this column is actually 4 times this column minus that column. 4 times this column minus that column. And so anyway, I can or something like that. There is a linear combination, and these two columns there are only two independent columns. All right, so these are the independent columns. And so taking the pseudo-inverse, we have a formula for that. Apply the formula. Here's the pseudo-inverse. I now use this to calculate G. So I multiply F pseudo-inverse times A, and I get G. So here's my G. Computing the pseudo-inverse of G, this is what I get for the pseudo-inverse of G. The pseudo-inverse of A is equal to the pseudo-inverse G times the pseudo-inverse of F, and gives me all of this. It's getting pretty hairy. The least square solution is equal to A pseudo-inverse times B, and so this is what we get. And so if I take A and multiply by this matrix, I get this, which is in fact B. So it shows that in this case we have an exact solution. In this particular problem we have an exact solution. So it's kind of rare that way. But anyway, we do. There it is. And the pseudo-inverse is in fact an exact solution. So whenever you have an exact solution, it's possible for there to be an infinite number of solutions. So we form the projector of A pseudo-inverse times A, so that we form the projector. We then form the projector onto the null space. So H is the projector onto the null space, I minus E, so this is what we get. And to find the orthogonal complement of A, I look for the independent columns of this matrix. In this case, these first two columns are linearly independent, so my A perp is given by that. The general solution, or all solutions to the linear algebra problem then, are given by this. X is equal to X star plus A perp times R, where R is this vector. So we have this is our solution for any R1 and R2. So I have an infinite number of solutions, and these are the solutions that I get. So these are some worked example problems. I hope they're helpful for you.